rate constant for the first order reaction at 460 degrees Celsius is 0.00023 seconds to the minus 1. The rate constant for this process at a different temperature is a different number. Calculate the activation energy for this reaction in kilojoules per mole with the hint that you're given the R value. Although I know this is the only R value we use this chapter. And I'm thinking about it. I don't know. On your final, you'll probably see some ideal gas law problems. And that's the only time, you use the other value of R. Now, in the last problem, we had the slope of this line, and we used that to find the activation energy. Now we have 2 points, and so we're going to use the 2-point slope formula. And the 2-point slope formula says, so the natural log of the rate constant at temperature 2 over the rate constant at the first temperature equals minus EA over R 1 over T2 minus 1 over T1. And I'm trying to think of where you will get this information. And I'm going to upload a new equation sheet, and it will have all the integrated rate laws. It has the the 2-point slope formula, the Arrhenius equation in 2 different versions. And you can see where we're going. We're going to be talking about equilibrium next. But it'll have all these equations on it. And most of these equations are on our summary of all rate laws as well. But here's the 2-point slope formula, and we're going to be solving for the activation energy. Let's go ahead and plug things in. And for me, I like to somehow circle things so I know they're together in my problem statement. Okay, and I'm going to call the one in red T1, K1, and I'm going to call the one in blue T2 and K2, because for me there gets to be a lot of numbers in these things, and I like to keep them separated. I'm going to plug everything in. I've got K2, which is 0.00083. I've got K1, 0.00023. I don't know my activation energy. That's E sub A. I know that this is 8.314 joules per mole Kelvin. And I've got my T2, which must be in Kelvin. So 510 plus 273. I get 783 Kelvin. $460 plus 273, 733. And just like that, I've got my whole thing set up, and there's only one thing to solve for, the activation energy. I'm going to start by working this left-hand side. .00083 divided by 0.00023. Natural log it. I get 1.28. And the other term here, so 783, 1 over that, minus 733, 1 over it. I get minus 8.71 times 10 to the minus fifth. Now, to find my activation energy, it's going to be this number times this divided by the 8.71 times 10 to the minus fifth. Oop. Let's try that over again. 1.28 times the 8.314 divided by, well, these two negatives are going to cancel out. So I'm just going to divide by this number in the positive sense. So divide by 8.71 exponent 5 minus. And I get 122,180. And I'm going to round that to 3 significant figures to give 122,000. That's going to be joules per mole. And let's see. It says report your answer in kilojoules per mole. And that's fairly typical because you want to compare your activation energy to your delta H reaction, say, which is also usually in kilojoules per mole. That's the activation energy for this problem. Anybody got any questions?